Welcome to qnawire.
Hi. So in this part of the problem, uh, we are given a combination of two capacitors. Let me draw the diagram first. So we have two capacitors like this. So capacitor C1, which is given to be 3 microfarad, and another capacitor C2, which is connected in series with C1, and the value of the capacitance is 5 microfarad. So we are given these two capacitors which are connected in series like this, and they are connected to a potential difference, a voltage source between the points A and B. So between these 2 points, we have a potential difference VAB, which is equals to the potential difference between the points A and B is applied to be 64 volts. So the potential difference between the points A and B is 64 volt, and the two capacitors C1 and C2 are connected in series. And in the first part of the problem, we are asked to calculate the charge on each of the capacitor. So as we know that in parallel combination, the charge on each of the capacitor is going to be same. So let's say the charge on capacitor C1, sorry about that. Let's say the charge on capacitor C1 is Q1. This is corresponding to capacitor C1, and the charge on capacitor C2 is Q2. So Q2 is the charge corresponding to capacitor C2. Now, we know that in series combination, the charge on each of the capacitor is going to be same. It is going to be equal to the total charge of the combination of capacitors. So our job is to find the charge of this combination, total charge of this combination between the points A and B. So before, in order to find that, we need to know the equivalent capacitance. So if I redraw the circuit, if I simplify the circuit, so after simplification, the circuit should look like this. So since C1 and C2 are connected in series, so we'll have an equivalent capacitor corresponding to C1 and C2 between the points A and B. So this is the simplified circuit, and we have a potential difference between these points A and B. And once we have this, we can find the total charge between the points A and B using Q equals P times C equivalent. So using this, we can easily find the total charge of the circuit, and which is indeed equal to the charge on each of the capacitors. So let us first find the equivalent capacitance. So for series combination, the equivalent capacitance is found in this way. So 1 over equivalent capacitance equals sum of the inverse of each capacitors. So 1 over C equivalent equals 1 over C1 plus 1 over C2. And in this case, C1 is given to be 3 microfarad. So this is 3 microfarad. And C2 is given to be 5 microfarad. And if we find this value comes out to be around 5.33 times 10 raised to 5 per farad. And in order to find the C equivalent, we need to take the inverse of what we have just calculated. So the inverse of the value we have just calculated equals C equivalent. And if you take the inverse of this value, the inverse comes out to be 1.88 times 10⁻⁻⁶ farad. So it's 1.88 microfarad. So this is the equivalent capacitance of this combination of two capacitors which are connected in series. So this is the equivalent capacitance which we have found. Okay, good. So we have found the equivalent capacitance. So our next job is to find the total charge. So total charge Q equals the potential difference between the points A and B, and the equivalent capacitance C equivalent. The potential difference between the points A and B is given to be 64 volts times the equivalent capacitance, which we found to be 1.88 microfarad. And if we calculate this value, the equivalent capacitance is going to be 120.32 times 10⁻⁻⁶ volt. So this is the value of the equivalent capacitance between the point A and B. So between point A and B, the equivalent capacitance, the total charge or the equivalent charge is equal to 120.32 times 10⁻⁻⁶ volt. And as we said that for series combination, the charge across each of the capacitor is going to be equal to the total charge of the circuit. So from that, we can say charge on the capacitors C1, which is equal to Q1, and the charge across capacitor C2, which is equal to Q2, is indeed going to be equal to capital Q, the total charge between the points A and B, which indeed is equal to 120.32 times 10⁻⁻⁶ volts. So this is the answer for the first part of the problem. This is part A. So having found the charge on each of the capacitor C1 and C2, the second part is asking us to find the potential difference across each capacitor. So for this combination of capacitors C1 and C2, we need to find the potential difference across each of them, potential difference across C1 and potential difference across C2. So let me redraw the diagram quickly here. So I have my capacitor C1 like this, then I have a capacitor C2 which is connected in series with C1, and I have these 2 points A, point A, and point B, where I have applied a potential VAB, which is given to be 64 volt. Now for series combination, the charge across each of them is going to be equal, but the voltage across each of the capacitor is going to be different. So let's say that the potential difference across capacitor C1 is V1 and the potential difference across capacitor C2 is V2, which we are required to find. So since for capacitors, we know the general formula, charge Q equals V C. We know the charge across each of the capacitor. We know the capacitance of each of the capacitor. We can easily find the voltage, the potential difference across each one of them, which can be given by, so the potential difference across capacitor V1, C1 is going to be equal to V1, which is equal to V1 equals the charge on the capacitor C1 divided by the value of the capacitance itself, C1. So which is going to be equal to, so charge was 120.32 times 10 raised to negative 6 volts. It's negative 6 coulomb. I'm sorry, I think I wrote volt here. It should be coulomb instead. So the charge, the units for charge is coulomb. So it's 120.32 microcoulomb. That's the charge. Divided by the capacitance, the value of the capacitor C1, which is 3 microfarad. So 3 times 10 raised to negative 6 farad. So doing this calculation, we'll find that P1 will be equal to 40 times 106 volts. So this is the value of the potential difference across the capacitor C1. And similarly for the potential difference across the capacitor C2, which is equal to V2, is given by Q2 over C2. Again, the charge Q2 is same, which is 120.32 times 10 raised to negative 6 coulomb divided by the value of the capacitance, which is 5 microfarad, 5 times 10 raised to negative 6 farad. And if you calculate this, the value comes out to be 24.064 volt. So this is the potential difference across capacitor C2. So we have successfully calculated the potential difference across the capacitor C1 and potential difference across the capacitor C2. And in order to verify if we have calculated our potentials correct, we can add the potentials P1 and B2, which should be equal to the total potential between the points A and B, which is equal to 64. And we indeed find that it is almost equal to 64. So